call that traditionally we use letters toward the end of the alphabet for functions. And you've been doing that since you took algebra, since they first introduced the alphabet into your math class. You know, let X be this number, let Y be this. So a lot of times letters towards the end of the alphabet for functions, and letters towards the middle of the alphabet for integers, or for what we're doing with sequences. And while I'm talking about the letters of the alphabet, a lot of times they'll use letters towards the beginning of the alphabet for what? Constants. Constants. So letters towards the beginning are for constants. Now it doesn't have to be this way. This is just the way math has evolved through the hundreds of years, through the 200 or 300 years. And anybody who's got a lot of math skills, they're going to pick up the book and they just automatically assume this stuff. So with that said, the problems we're doing in chapter 11 with sequences, so I could say this, in chapter 11, section 11.1, we had this problem. We had this problem. This was yesterday. F of n is 1 over 2 to the n. And when I see the n, I'm thinking, okay, integers, sequences, and I could graph this. In fact, let's write a few terms of this. What would this be? When n is 1, it's what? 1/2. What about when n is 0? It's 1. And I could say n is -1 if I wanted to. When n is 2, it's what? 1/4. When n is 3, it's 1/8. When n is 4, it's 1/16. So I could graph this. N F sub n, and I will say when n is 0, I had 1. When n is 1, I have 1/2. When n is 2, I had 1/4. When n is 3, I had 1/8. When n is 4, I had 1/16. And you get this, for sequences, you get this graph that's just some dots, because the only acceptable values for n are the integers. However, if on the other hand I had f of x is 1 over 2 to the x, well, I got the same values on those integers, but this time I would do what? I'd connect the dots. This is a continuous function, but this is just the dots. So, in fact, you might have heard the word discrete, where they're just the dots. If I have a function that's continuous, 0, 1, here, 1, 1/2, 2, 1/4, 3, 1/8, and what if I did pick -1? I would get 2, And this is a continuous function. Now, I like to mention that to you because in chapter 11, we can take some problems that are modeled with a sequence. We can model them as this continuous function, and whatever applies to the continuous function will probably apply to the sequence. We can model it back and forth if we need to. And some of the theorems in chapter 11, they do that. So, wanted to mention that to you. All right, let me get rid of, oh well,